Okay, so good morning, everybody. Welcome to the latest edition of the Pangolin Seminar. Today, Dmitry Faifman of Tel-Aviv University is going to talk to us about intrinsic volumes of submanifolds of normed spaces. So, over to you, Dmitry.
Okay, thank you for the introduction, for inviting me. Also, let me start by apologizing. I didn't find a solution for my dog. So in case there's barking, I have a bag of bribery here, but it will be a minor distraction, hopefully. Okay, so let's get started. Right. This is going to be about joint work with Thomas Wanner. And most of it will be actually crash course in evaluation theory with the last few slides dedicated to this particular application. But of course, that's the more important part. So maybe it's not a bad thing. Okay, let's start with the classical background. By K over N, we will denote the compact convex bodies inner N, and we equipped them with the Hausdorff metric topology. Bn is going to be the Euclidean unit pole, and we denote it by its volume by omega n. So here come the main heroes of the story, the intrinsic volumes. Those are mu k, they're functions of convex bodies. K ranges between 0 and n. What are they? Well, some of them you definitely know. The zeroth one is the constant one. The n minus first is the surface area up the multiple, and the nth one is the volume. So what are all of them? Well, there are different ways to think about intrinsic volumes or to define them. Here are some of them. The Steiner formula uh, tells you that if you take a convex body and consider its epsilon extension, or its Minkowski sum with the epsilon Euclidean pole, its volume is going to be a polynomial in epsilon. And the coefficients of this polynomial, when you properly normalize them, are the intrinsic volumes. Okay, if you write this explicitly for sufficiently smooth bodies, then what you'll get are integrals over the surface of the body of the elementary symmetric polynomials in the principal curvatures of the convex body. So for example, if you plug in k equal to 0, what you get is the integral of the Gaussian curvature, which we all know is a constant for convex bodies. Okay, from a different perspective, an integral geometric perspective, you can define intrinsic volumes as by Crofton formulas. What are those? Well, you consider the affine Grossmanian of all n minus k dimensional affine planes, denoted E. You intersect them with k, and you take the Euler characteristic of that. Okay, so it's going to be either 1 or 0, because k is convex, but in the future, at some point, k will no longer be assumed convex. For now, it's either 1 or 0. And you integrate this function over all over the affine Grassmannian. And that's going to be the same thing. And proving it directly is not so easy, but luckily there is yet another characterization. But for this, we need the notion of evaluation, which will be central to this talk. So let me introduce it. Evaluation is a finitely additive measure on convex sets for now. Namely, the inclusion-exclusion principle holds. Whenever K, L, and their union is a convex set, you want this relation to hold. By the way, I have no indication that anyone is hearing anything I'm saying. Can someone indicate that?
Yes, we're hearing
Thank
you.
you, thank you, thank you. Thanks. Okay, so with the notion of evaluation in mind, here comes yet another way to define intrinsic volumes in axiomatic way, which is due to Hadwiger. So if you consider a rigid motion invariant continuous evaluation, which is also K-homogeneous in the body, then it must be the Kth intrinsic volume up to a constant. So that's a nice theorem, and that immediately allows you to establish the equivalence of all the other ones. Okay, very good. So let's talk a bit about valuations. Clearly, they are important. By this val of Rn, I will denote the space of all translation invariant continuous valuations, but I am no longer saying rigid motion invariant. So that's a bigger space, in fact, much bigger. There is a natural norm, well, a natural norm topology on the space. You consider just the supreme norm of all convex bodies contained in some Euclidean ball, but so you can get different norms by choosing B differently, but the topology is the same. And here are the few things we need to know about valuations for this talk. The first is the Macmillan decomposition, that valuations, they come in different degrees of homogeneity. Those degrees of homogeneity must be an integer between 0 and n. So we have this direct sum decomposition, and yes, this is how I denote K-homogeneous valuations. And there are simple descriptions of the end spaces. So for zero homogeneous valuations, there's just the constants. And the n homogeneous valuations, there's just the Lebesgue measure. So this is not a completely trivial statement. It's a theorem due to Hadwiger. Also, I will be saying sometimes densities instead of Lebesgue measures. Right. So those were one-dimensional spaces.
So are the val k just the k-dimensional Hausdorff measures?
No.
No.
So there's a lot more. It's an infinite dimensional Banach space. K-dimensional. I'm not sure I even understand your question. So what is a K? How do you? No. So what you said is not an example of valuation, right? If you try to apply it to an n-dimensional convex body, you'll get infinity, right?
True.
Mm-hmm.
No, so what is val k?
So an example would be the kth intrinsic volume.
Okay.
That would be the first example. Another maybe simpler example, though less natural, is project your body to a k-dimensional plane and take the volume.
Okay.
That's a k-homogeneous valuation. Okay. And one final fact is a theorem due to Klein. So suppose that you have a k-homogeneous valuation, which is also even. So it's invariant under the antipodal map. Then what you can do, you take your valuation, you restrict it to all linear subspaces, just consider it applied to convex sets in a given k-dimensional plane for all planes. So when you restrict a k-dimensional plane by this theorem of Hadwiger, you'll be getting just some Lebesgue measure on this plane, right? It's k-homogeneous on a k-dimensional plane. The collection of all those Lebesgue measures uniquely determines the valuation. You should note that it's wrong in the opposite direction, namely if you just prescribe some collection of Lebesgue measures, chances are it will not correspond to any valuation. There's a particular subspace of such collections that correspond to valuations. Okay, so that's the background from the classical theory. And now we pass to a more modern theory of valuations due to Olesker. Again, I will also only give the crash course that will be relevant to us. So there is the notion of a smooth valuation. This is a subspace of val. So it's denoted val infinity inside val. And this is a purely representation theoretic notion, but let me spell it out particularly for the space of valuations. So we say that the valuation is smooth if, when you consider its orbit map, which is the map from GLN to the Banach space of evaluations, which just acts naturally on the evaluation, then this map should be a smooth map. Two examples that we've seen, the case intrinsic volume happens to be smooth, but for instance, the other example we had is not smooth. It's easy to convince yourself that if you are in the plane and your evaluation is project to the line and take the length of that, then when you say start with an interval and you rotate it, you'll be getting something like the absolute value function. That's not smooth, of course. Okay.
Excuse me, Dmitry.
Yes.
So is the intrinsic volume of the smooth convex body a smooth valuation?
So there's no need to say a smooth convex body. Evaluations are at this point, their function is on all convex bodies. And yes, the case intrinsic volume is just a smooth evaluation on all convex bodies.
Oh, yes, sure.
Yeah, and here is a key construction of Lasker that connected evaluation theory to integral geometry in a very fundamental way. The product of smooth evaluations, so it respects degrees of homogeneity. And let me indicate, well, give you an example, but a main example of how this product is defined. So consider evaluation which is given by a Crofton integral, which is similar to the Crofton formula we had before, except instead of taking the Haar measure on the affine Grassmannian, which is invariant under the rigid motion, I just take some measure, the one which is assumed translation invariant, so that I get a translation invariant measure, evaluation, but it's no longer assumed rotation invariant, right? Some measure can get a lot of evaluations like this. So we have two evaluations of this form, phi and psi, that corresponds to two different measures, mu1 and mu2. Let me just say that those are not intrinsic volumes. Sorry that I used the same notation, just some measure on the affine Grassmannian. Then the product is defined by distributivity as you would expect. And when you need to take a product of this inner thing, which is the Euler characteristic of the intersection with the given affine plane, you just intersect the two planes. So and you take the integral over the product of the Grassmannians. Of course, you can reformulate it by saying that you have two measures on the affine Grassmannian, and you consider a map from the product of the Grassmannians to this new Grassmannian of codimension I plus j, and the product is the push forward of the product measure under the intersection map, which is almost well defined. Well, that's the formula anyway. And the key thing to take out of that is that the product of evaluations is intimately related to intersections.
Excuse me.
Sets. Yeah.
Did I understand correctly that every smooth valuation can be written as this integral with respect to some measure mu on the affine Grassmannian?
That's a very good question. That's correct for every even valuation. So of course, those valuations are all even, and yes, all even smooth valuations can be written like that. That's a highly non-trivial theorem, which is a consequence of Lesker's irreducibility theorem.
But why is every smooth valuation an even valuation?
No, that's false. What's true is that this integral is an even valuation because because subspaces are invariant.
But this is also a non-trivial fact that the smooth valuation is even.
No, that's false. There are smooth valuations which are odd. But
then you
it's
define...
just that right. So I just explained how to take products of even smooth valuations. Yes.
I see.
And I was not even going to say that every even valuation can be written like that. I was going to say that's just an example. But yes, you're right. All even valuations have this form, and you can define product like this for even valuations.
All right, thank you.
Okay, and as an example of a computation of product, the kth power of the first intrinsic volume is the kth intrinsic volume up to a constant. And that, for instance, follows from Hadwiger's characterization. Right? All the operations are natural, so this is rigid motion invariant. So clearly, it must be the kth intrinsic volume. Okay, and now we're passing to manifolds. And for this, we'll need to talk about the normal cycle. So I will talk in slightly less generality than full generality, but you will forgive me. M is assumed a smooth oriented manifold, and we will have some Riemannian structure fixed on it, as M will stand for the sphere bundle. And we need some collection of test bodies to replace convex sets. So for us, P of M will be differentiable polyhedra. So notice how there's no assumption of convexity here. It's not the only possible choice, but good enough for us. Okay, and let me define the normal cycle. Basically, it generalizes the notion of a normal bundle. So let me first read what's written here. The normal cycle is a subset of the sphere bundle. And a vector lies in the normal cycle if its product with gamma dot is non-positive for any gamma that starts at this point x and stays inside the set for small values of t. So basically, it's a normal that's pointing outward. If you have something like a corner, then you have the full cone. So I have here the pictures. You've been seeing a lot of normal cycles recently all over the place. That's what they look like, pointing outward. And notice that it has a fixed dimension, n-1, which is independent of the dimension of k. Somehow, if you have more of the base manifold, then there are less normals, right? And it works together to give you a Lipschitz submanifold of the sphere bundle, which has dimension n-1. And its key property for us is that it's a evaluation. If you consider it as a functional on differential forms, which it is, you can integrate over it, then it satisfies the inclusion-exclusion formula, at least when x and y are sufficiently nice with respect to each other.
Sorry, what does that double square bracket mean?
It means that you take an oriented manifold and start thinking about it as a current that is a functional of differential forms.
Ah, okay.
It really doesn't do anything. Okay.
Sorry, can I ask something?
Yeah.
What is a polyhedra in the Riemannian setting?
It's something that locally is diffeomorphic to a piece of a polyhedron in Rn.
Aha, okay, thanks.
Okay, so here comes the definition. U, which is due to Simon Lasker and Joe Fu. You start with a pair, a measure on M, mu, and an n-minus form on the sphere bundle, and you make a smooth evaluation, phi, out of it, and it's going to be functional on the differentiable polyhedra, which is given by a sum. So the two summands are called the interior term and the boundary term for obvious reasons. The interior term is when you integrate over the interior of the body, the measure mu, and the boundary term is when you integrate the form over the normal cycle. The normal cycle, as you have seen in the picture, only sees the boundary of the set. That's the interesting summand. This one is just to make things more natural. And yeah, this is the interesting part. The motivation behind this definition is once again a corollary of Lasker's irreducibility theorem, which says that in linear space, you can identify translation invariant smooth valuations, which we just defined, with the smooth translation invariant valuations that we were discussing earlier. So of course, those are functionals on convex sets. At least at first, those are functionals on polyhedra, but they're naturally the same space. Okay. A little bit more about valuations on manifolds. So we no longer can't talk about homogeneity, but there is a filtration that generalizes homogeneity. W0 is everything, Wn, something which you should locally think of as. And homogeneous valuations, those are just measures. That's when you have just mu, not no omega, just the interior term. And well, Wk is when you work with a form that when you write it in coordinates, it has dx1 to dxk, and the other parts of the form come from the vertical fiber. And the relationship to homogeneity is the following: the associated graded algebra is just the associated graded space is the space of sections of the bundle of k homogeneous valuations on the tangent spaces. Okay. And here again, we have a fundamental structure of product due to Lasker. So there is a product, it respects the filtration. And moreover, you have something like a Poincare duality. So you can pair two valuations by taking their product, which I haven't yet defined, but you take the product and you evaluate on the whole manifold when it's compact, and what you get is a non-degenerate pairing. And also, when you have one manifold embedded in another, then this product is natural with respect to restriction. Restrictions are homomorphisms of the structure. Okay, and here again, let me indicate how to define this product. So consider some fixed set A, and consider this valuation chi A, which evaluates the Euler characteristic of the intersection with the set. That's not a smooth valuation in the sense that, well, it's not a smooth valuation. It's clearly somewhat discontinuous, but it's a valuation at the same time. And if you just insist on this identity, that the product of two such valuations corresponds to their intersection, then you can translate it to smooth valuations pretty much how you did it. We did it in the linear setting by considering Crofton formulas. You can produce a smooth valuation out of such discontinuous valuation by integrating over a bunch of different. So that's not really a definition, but that's the proper way to think about it, or just one good way to think about this product. And once again, this product structure reflects, as you can clearly see, the intersection of sets, and thus intimately tied to things like kinematic formulas, the integral geometry, according to the Blaschke school. Okay, I think that's all the background in evaluation theory, and we can talk about intrinsic volumes in this setting of Riemannian manifolds. So first, the theorem that appeared first is due to Weil, and Weil noticed that the following remarkable thing. You take a Riemannian manifold, say a closed Riemannian manifold M, and you embed it isometrically in some large dimensional space. You can use Nash theorem to do it, and you consider the epsilon extension around this manifold, and you take the volume. Once again, what you get is a polynomial, at least for small epsilon. So that's nice to know. That's not that difficult to prove, as Weil, well, at least for Weil here, right? So far we did only what a school child can do or something. But then he noticed that those coefficients, if you properly normalize them, don't depend on the second fundamental form. They're invariants of the induced metric and nothing else. And that's remarkable. I think to this day, we don't, the only proofs there are computational. It's not a great explanation of why that is, but they're intrinsic invariants. And using the language we just learned, we can say the following thing. For every k, there is an assignment, mu k, that takes a Riemannian manifold M with metric G and produces a smooth evaluation on this manifold. And this assignment, well, first of all, it's k homogeneous in the metric, so it measures things in meters to power k. When you evaluate mu k on some subset of your manifold. And it's the property that Weil described is that whenever you have an asymmetric embedding of M inside N, the restriction is what it should be. So that's a translation of Weil's theorem into valuation language, combined with some results of Chern. Okay, so once again, the examples that you know are very simple. Mu0 is just the Euler characteristic. Mu n is just the n-dimensional volume, and minus mu n minus 1 is the.
So Dmitry, I have a question about that. In the Weil formula, every second mu k is 0. And
right. So when you have a closed manifold and you compute its own intrinsic volumes, half of them are going to be 0. Yes. Was that your question? But if you, so in this first box here, half of the coefficients are going to be 0. That's true. But
yes,
if you,
then you have, I'm sorry.
but if you think of Mk as functionals on subsets of M, which can have boundary, for instance, then none of them are trivial.
Yes, I see.
Right. So we also have the surface area. And just in terms of terminology,
so Weil's theorem doesn't assume smoothness of the embedding at all.
It does. So
right.
It surely needs C2. I don't think you need more than that, but I don't know.
Okay.
But it definitely needs C2. I was assuming C infinity here.
Okay.
Yeah, for C1 it's just wrong. It would be just plainly wrong. Okay, I am committing myself to something that might. Definitely all the proofs I know assume C2 very strong. I would be surprised to learn something stays for C1. Okay, so the Weil principle is basically when something like this happens, when you have some structures and manifolds, and you can assign evaluation to the structure or some valuation, and it is respected by isometric embedding. So this phenomenon has been observed in some settings to date. For instance, it's been established to the Riemannian setting in contact manifolds, which is very non-metric setting at least, and also in Keller geometry it's been worked out these days. And there are some conjectures about possible extensions to Alexander spaces, but it's mostly conjectural. Okay. Let's move on. Yeah, let's spend a couple of minutes on spelling this out explicitly in one example. So let's work with a closed-oriented Riemannian manifold and discuss the Chern-Gauss-Bonnet theory. So the first point here is that you compute the Euler characteristic by integrating over M the Faifman of the Riemannian curvature form. So that's That was Chern's theorem. This is you should think of as the interior term of evaluation. So a couple of years later, Chern also found a boundary term. So there is a canonic form omega k, or omega kappa, which lives on the sphere bundle, such that whenever you have a reasonable subset of your manifold, you can compute its Euler characteristic by by this explicit formula. You integrate the Faifman over the interior of X, but you also integrate over the boundary this form. So for instance, for manifolds with boundary, this would correspond to the geodesic curvature of the boundary. Okay, let me just mention that you can also write this for all the other intrinsic volumes. And the things you get are called the Lipschitz scaling curvatures. Again, a bit complicated expressions, but very explicit. Okay, and those are intrinsic expressions for the intrinsic volume, of course. Okay, and now we come to the subject of this talk, which is intrinsic volumes in norm spaces. So let's start with a norm space. I will always assume the norm is smooth and strictly convex. And the first question to ask is how to measure volume in a norm space. So depending on your background, I guess what I'm going to say is going to range between trivial and well-known, trivial and new, but I should say it anyway. So how to define volume? The first probably thing to try is just to take the unit ball and say, okay, let's call this volume omega n, same as the volume of the Euclidean ball thing. What you will get is just the Hausdorff measure, and that's a good choice for some purposes, but from certain perspectives, particularly if you're interested in something like symplectic geometry or dynamics, or alternatively, as we will see, if you're interested in integral geometry, a better definition is that of the Holmes-Thompson volume. So once again, what we need to do is to normalize the Lebesgue measure. So we need to say what is the volume of the Euclidean ball, of the unit ball, and you declare it to be equal to the Mahler volume of the unit ball, which is the volume of this product of B times B dual, and with some constants. Constant is just to keep it consistent with Euclidean structure. And so this is the symplectic volume. That's what you would get if you consider the Liouville volume on the unit co-ball bundle and you push it forward to your space.
Excuse me,
Yes?
is this space finite or infinite dimensional?
Finite.
Finite. So n is a dimension.
Yeah.
Right.
Thanks. Mm-hmm. Yeah, no, everything is finite dimensional. And okay, and two trivial remarks. If you have a subspace, then of course it inherits a norm. It's a norm subspace. And so you can construct the Lebesgue measure of this norm on this subspace. You get the density on this subspace. And for instance, if you have some k dimensional submanifolds, then you can compute its k dimensional Holmes-Thompson volume by integrating over it. A trivial remark. And the natural question to ask is, can we extend it into evaluation, something that can be applied to n-dimensional convex sets, for example? Yes, the answer is yes, specifically for the Holmes-Thompson volume. That's a result of few people. That in fact there is this mu k with subscript f, which is a smooth k homogeneous evaluation. such that when you restrict it to a k-dimensional subspace, you just get the Holmes-Thompson volume there. And let me say that essentially by definition, it will have this linear while property in the sense that if you restrict it to a subspace, then you get the corresponding intrinsic volume on this subspace. The reason is Klein's theorem, that evaluation is determined by its restrictions to subspaces of dimensions which are its degree of homogeneity. Since those are just the Holmes-Thompson-Lebesgue measures, so everything here is unique. Let me skip this construction.
Is the norm supposed to be symmetric in this case, or can it be asymmetric?
It's a very good question. So I don't see any. Here I only discuss symmetric norm, but I would expect you can do things also for non-symmetric.
And so this Klein theorem that you just
yes, that's pure, yes.
Okay.
So once you restrict yes, you lose all the other information once you restrict a k-dimensional subspace. But I think something can be said about non-symmetric norms, but here we only discuss symmetric norms.
Okay.
The one thing that I want to say that once you construct the first intrinsic volume, which is really straightforward, you can do the case intrinsic volume as in the Euclidean case by taking its case power in the sense of a Lesker product, properly normalizing it so that it's consistent with the definition of Holmes-Thompson volume, and you got some intrinsic volumes. It's not by no means obvious that it can be done, but the uniqueness is completely straightforward. And let me also remark that this is not the same as considering the volume and taking the coefficients. That will give you something very different. Okay, so once again about uniqueness, if you assume that what you want to work with is the Holmes-Thompson definition of volume, then there's just one way forward, and you just hope it works out, and it does. For instance, if you take the Boozman definition of volume, it's not even clear that evaluation can be defined like that. But in fact, if you also insist on multiplicativity, then you don't need to make any assumptions. The first intrinsic volume really is independent of the definition of volume, right? The size of an interval just depends on the norm, and then multiplicativity gives you all the other intrinsic volumes. Great, so now we believe there is an extension of intrinsic volumes, which is sufficiently reasonable in general norm spaces. And we want to talk about submanifolds. So you all know what is a Finsler manifold, so I'll just read it. It's a manifold where you have also a norm on every tangent space instead of a Euclidean product, as you have in Riemannian manifolds. You have just some norm, which again I assume smooth and strictly convex everywhere and symmetric. And the question that was asked by Joe Fu is, does the while principle extend to the setting? Namely, suppose you have an asymmetric embedding of a Finsler manifold into a norm space. Then, is the restriction of the kth intrinsic volume an intrinsic invariant of the Finsler structure? And in some cases, the answer is a trivial yes. For instance, if your manifold is a surface, then you can just write explicitly what those things are. And they are clearly intrinsic. Zero is against the other characteristic. The first one would be just the length of the boundary of the set, and the second one would be the area of a subset, clearly intrinsic. But in general, the answer is no. That's our result with Thomas. That the first counterexample there is, and in fact that we give, and also the smallest one that can be given, is that there is a three-dimensional Finsler manifold and two asymmetric embeddings into six-dimensional Finsler space, norm spaces that give you two different intrinsic volumes, two different restrictions of the corresponding intrinsic volumes. So we don't have a while principle in this setting. And okay, why do we still have so many slides? And okay, is it a no-go result? Well, yes and no. We still discovered that in some weak form, the while principle does hold, and that's what I'm going to talk about now. So let me introduce the weak while principle. First, a global version of it. We will say that a manifold, a submanifold M in a linear space V satisfies the global weak while principle if whenever you have two norms on the space which restrict to the same Finsler structure on the manifold, then the corresponding intrinsic volumes restrict to the same valuation on your manifold, which then one might want to call the intrinsic volume of the manifold. So that's a property of a manifold inside the linear space, no metric attached to it. Well, a trivial example is, for example, when you have a compact hypersurface, then any line in your manifold, in your space, is tangent to your manifold somewhere. That means that you know the norm on this line, which is the same as the Lebesgue measure on this line. And by Klein's theorem, you can reconstruct the valuation on the whole space. And that means that you also know its restriction to the manifold. So this is a trivial example when the global weak while principle holds. But that also tells you that this is not a very good definition. Somehow, you don't want to be using information from one point to on the manifold to make conclusions about other areas of the manifold. So this is why we introduced the local weak while principle. We will say that the weak while principle is satisfied if the GWWP holds for all open subsets of a manifold. So this is a stronger requirement. Okay, and here is a result here. It's a trichotomy. So we have a manifold of dimension M that sits inside an n-dimensional space. First, if the codimension is small, if the codimension is at most 2, then we find that the weak while principle holds. So whenever M is a hypersurface or codimension 2, then there is this weak intrinsic property of the intrinsic volume. When the codimension is intermediate between 3 and when the full dimension is between M plus 3 and twice the dimension of the manifold, then we have the weak while property generically for generic embedding, immersion, but you can find counterexamples, and I will even give you one. And when the codimension is high, then weak while principle fails completely. Generically, you never have it. Okay, that's the result. I think that's a good point to stop and to ask if you have any question about the result.
I'm fine. Just so you know, Dmitry, you've got 20 minutes, okay?
Okay, thank you. 20 minutes, wow.
Yes.
So
We started a bit later, so my watch is saying 42. So you've got 18 to 20 minutes.
Okay, thanks. Okay, and now let me talk a bit about the ideas that go into the proof of this. A few simple reductions. First, notice that we don't need to talk about all the intrinsic volumes. It's enough to talk about the first intrinsic volume, degree of homogeneity 1. Why is that? Because of multiplicativity, because restrictions restrict the respect the Lasker product, it's enough to talk about the first intrinsic volume. If its restrictions are intrinsic, then their powers are intrinsic, and if they're not, well, that's bad. Okay, so we only talk about mu1 from now on. The other piece of preparation, we will fix a Euclidean structure on the linear space. It has an induced Riemannian structure on the manifold, and there are corresponding contact forms on the sphere bundles. And we also have the second fundamental form, which is a symmetric form on the tangent space with values in the orthogonal complement, the normal space, and it will be denoted by H. Okay, so there, by a theorem of Berenick and Brocker, okay, by a trivial part of the theorem of Berenick and Brocker, there is a natural inclusion of the space of evaluations inside this product space of functions on M and M forms on the sphere bundle. So M is the dimension of the manifold. So it's easy to understand what is this map. Recall that evaluation is given by a pair of forms, the form on the manifold and the form on the sphere bundle. And we also have the Lasker-Poincare duality, which tells you that evaluations are essentially dual to themselves. So if you take the dual of this map, you obtain this map. The result of Berenick and Brocker describes precisely which pairs you get, but it's not important for us right now. So a function and an M form on the sphere bundle. An evaluation can be described by this pair. Okay, so first we can go ahead and just compute this description for the first intrinsic volume of a linear space. That's a simple computation. And you find that, well, that's what it is. F is the norm. So you take the inverse cosine transform of the norm, some function on the sphere, and you multiply it by some standard form, the contact form times the volume form on the sphere. Okay, so that's the meaningful part, the inverse cosine transform of the function.
Just a second. What is the cosine transform?
Oh, I'm glad you asked. I have an answer prepared right here. That's integral transform from functions on the sphere to themselves, which is given by this formula. You integrate the absolute value of the inner product. That's the Schwarz kernel. Okay. That's the formula.
Thank you.
And well, it appears frequently in integral geometry. It's closely linked to the Redon transform on the sphere. And, yeah. Okay, so we have this description of our evaluation. And the next thing to do is to restrict the evaluation to our submanifold and carry out the restriction explicitly in terms of this description. Now that's a bit of a headache, and I don't want to abuse my 20 minutes to torture you, but there is a standard, a standard way to describe such things. It more or less follows the description of the Chern-Gauss-Bonnet theorem for the boundary term. So basically, you consider the bundle of orthonormal frames. You look at it as a bundle over the sphere bundle by the U0 vector, the zeroth vector. And well, that in that way forms on the sphere bundle. You can think of them as a subset of forms on the space of orthonormal frames. of course, once you have a form on the full bundle of frames, you should start thinking, does it represent a form of the sphere bundle or not, but gives you flexibility. And on this frame bundle, you have a lot of standard forms. There are the whole Cretan apparatus. You have the solder forms, ETJ, and the connection forms, omega ij, and the curvature forms, which we don't need here. Okay, I don't want to nail down all the notation. What we should take out of that is that we can represent the restriction of the evaluation in terms of all those standard forms with some coefficients. And those coefficients is what we need to determine. If those coefficients turn out to be intrinsic, then good. If not, then bad, basically. You follow the restriction, you get formulas, some integral formulas for those coefficients. And it's not clear whether it's intrinsic or not. Of course, we introduce some auxiliary Euclidean structure, which sits here and also here, and need to check if it cancels out or not. So something big and scary. We need to understand if it's intrinsic. One thing to note is, so maybe I will just read what's written here. There is an integral over the sphere in the normal bundle, another integral over an angle. Well, phi is the angle, n is the point in this sphere, and this is some minor in the second fundamental form, segment over some multi-indices. So there is some minor, you get a matrix like this, and then you take its determinant. Right, this is the inverse cosine transform of f evaluated at this point on the sphere. Scary stuff. And one thing to note is that the dependence on the norm is actually linear. So it's not really important that f is a norm. Things would work basically for any function. Okay. How much time do I have?
10 minutes.
10 minutes. With 10 minutes, yeah, I can read it. So by theta, I will denote this obvious map, which takes a point on the sphere bundle and just forgets the base point. The Gauss map, I guess it's called. And, similar to the Gauss map, just forget the point. And we have the cosine transform. So a first simple computation you can make is that the zeros coefficient is just the inverse cosine transform in the tangent space of the manifold. So you take the norm, you restrict it to the sphere, and you take the inverse cosine transform. So that's clearly intrinsic coefficient. And basically, this coefficient doesn't know about the curvature of the manifold. You would get the same thing for a flat m-dimensional thing. That's also why it's immediately clear that it's intrinsic, because in the linear category, we definitely had intrinsicality of our intrinsic volumes. Okay, so for the zeros coefficients, all is good. It only depends on the values of the norm on the image of the sphere bundle under theta, on knowledge of f on all those units, on all those points on the sphere which occur as unit tangent vectors to the manifold. Okay, very good. What about the other ones? Well, with the first coefficient, so if you carry out some tedious computation, it turns out that you can express it in this form. Oh, here is another integral transform on the sphere, the hemispherical transform. Again, very much related to the cosine transform, Dredon transform. This one is more interested in odd functions, actually. So you integrate around half the sphere. And this is a function of the center of the half sphere. That's the hemispherical transform. And turns out that the first coefficient is the inverse hemispherical transform of something that depends on the gradient of the norm. So that's bad news for intrinsicality, because the gradient needs not only the values, but also some derivatives. And okay, but it could be that derivatives are encoded in the values. So let's study that. The key observation here is the following one. If you have a vector in the normal bundle to the manifolds, and you want to know the derivative of this function, the norm, on the sphere in this direction, then sometimes it is encoded by the values of the function on all unit tangent vectors to the manifold. When? Suppose that this direction happens to be the second fundamental form at the pair, and one of the vectors here is the point you're interested in. Well, what you can do, you can consider a curve on your manifold, starting at this point, going in the direction v, and consider the parallel transport of u along this curve. And then you look at the values of the norm along this curve and take the derivative of that. And basically, by definition, you recover the derivative in the normal direction. That's what second fundamental curve, form does. Right? It takes the derivative of the tangent vectors and looks in the normal direction. Okay, but there is a fine point. You need one of those vectors to be the point you're interested in. And it's not the same as just the whole second fundamental form. If you look at the image of the second fundamental form at the point, then generically it's a rather large subspace of all normal vectors. But if you fix one of the vectors to be a point you are interested in, then smaller, generically. And that should give you a good idea of why large codimension is bad and small codimension is good. For instance, when n is now greater than 2m, then at least generically they are the same, and that's more or less what you need to.
Right, can I just ask a question then?
Yes.
Because I mean, this is the thing. So genericity in general is a question of surjectivity. Somebody is surjective. So the surjectivity or not is coming from this stuff that you haven't read here. Is that right?
I'm sorry. Surjectivity.
As a general rule, the genericity of any property is determined by the surjectivity of some
Yes,
sort
yes,
of
yes, yes. The surjectivity of the map theta.
Right. So, and that's coming from these dimension estimates that you haven't read here.
Yes.
Right. Okay.
Okay. That's basically the key idea. From now on, there's mostly some analysis with, okay. The small codimension thing is the extra, is where extra tricks are needed. But at this point, we understand fairly well why generically under this condition we have weak-well principle, and under this condition the weak-well principle generically fails. So in this high codimension, basically any generic thing is a counterexample. But let me also tell you how to build a counterexample in intermediate codimension. It's going to be a 4-dimensional manifold in an 8-dimensional space, which is given by the Segre embedding. Let me skip the coordinates for definition, just tell you in coordinates what it looks like. So this is M4. This is how it's parameterized. This is an R8. And what is good for us because it kind of mimics what a thing in large codimension does. So the image of the second fundamental form at a point is almost always, well, it's always larger, and the other thing that we need for technical reasons is that this number here is constant for almost all u. And that's basically how you can construct a counterexample. Right. Okay, and how much did I have? 5 minutes?
Basically, it's about you've reached 1 hour, but I guess nobody will mind if you speak for another 5 minutes. I'm enjoying
Okay,
talking.
I'll try to squeeze it in 2 minutes.
Okay.
Okay, so what about the other coefficients? So far, I only showed you the first coefficient, but in fact, you can show that the kth coefficient depends on k derivatives in all kinds of directions of the second fundamental form. So basically, if you, once again, confirming that if you can recover the second fundamental form by fixing one of the vectors, then that's all you need. What happens in small codimension? So here there are 2 tricks. One is from linear algebra and tells you that if you have a symmetric form and the image of the symmetric form in the space is at most 2-dimensional, that in fact for almost all vectors you have this identity. So that's a good indication that there is hope that in codimension 1 or 2 you can get more than just generic validity. And in fact for m+1 that's all you need. For m+2 there is one extra piece from differential geometry. And here is the piece. If it turns out that your second fundamental form is in fact of image 1, of dimension 1, then there's 2 possibilities. Either you locally lie in a hyperplane, or as a quadratic form, it has rank 1. Okay, so this is already a very strong constraints, and with that you can work through the formulas and deduce that you have intrinsicality. Okay, I guess I will just stop here, and thank you for your attention.
So everybody, please unmute your microphone so that we can find.
And I will mute mine for poetic justice.
So, just a second. Let me see. Oops. So, are there any questions for the speaker?
Maybe I have a question.
Go ahead. Go ahead.
So you used this auxiliary Riemannian structure. Is it a hard calculation to show that the whole procedure does not actually depend on which auxiliary structure you take?
Yeah, I said at some point something that I regretted saying. Let me clarify. What the weak while principle says is that if you change the norm, the norm, as long as it induces the same Finsler structure, then the result doesn't change. The expressions we have very much do depend on the Euclidean structure, but it's auxiliary and it doesn't change as you're changing the norms.
I see. But so basically you do need two structures, one Finsler and one Riemannian structure.
I don't, yes and no. To do computations, I use the Euclidean structure, but the actual evaluation we get does not depend on it. Only this expression in coordinates depends on the Euclidean structure.
Okay.
Right.
Are there any other questions? There's always a bit of a lag in Zoom. You have to wait about 10 or 15 seconds.
Oh, seconds. I thought you were going to say minutes. That would
no.
correspond to my yeah.
It's easy to forget that we're all in different parts of the planet, so there's always that old delay that just comes from limitation of the speed of light. So any other questions?
So maybe I have another one. So I'm not.
Go ahead. Go ahead.
I'm not an integral geometer, and I'm mostly interested in the other definition, the Busemann-Hausdorff definition of volume. Is do you have any results there? I remember you mentioned something that this multiplicativity is not rules
Right.
out
So,
the Busemann-Hausdorff.
the disappointing truth is that I know very little about integral geometric properties of the Boltzmann volume, and not only me. It's simply unknown whether there is a collection of evaluations that corresponds to the Boltzmann definition. So in some low-dimensional cases, it's true by the wrong reasons. So for instance, you can always find the first intrinsic volume. You can always find the one homogeneous population such that its restriction to lines or just the norm, and it's unique, and you can study it. Nobody has done it. In higher degrees, it's simply unknown if you can do it.
Okay. And so you had these, I think you called them Crofton formulas. So this is like another way how to define the intrinsic volumes, right? So you take the integral of all affine planes of the Euler characteristic, right? So because in my work I have something similar. I have that the Busemann-Hausdorff volume I can write as the Radon transform of the Finsler norm to some power. And so it's interesting because some of the formulas looked at least familiar in some sense.
Well,
I mean, this is not really a question I'm posing, so yeah.
Right. Yeah, I would love to know if the Boltzmann volume can have some meaningful integral geometry. One result that I'm aware of is of Schneider, that some norm spaces don't admit a Crofton formula for the Boltzmann volume, where the Crofton measure is positive. But it might well be that a non-positive measure would do the trick. It's just unknown.
I see. So this is Schneider, you said? Okay. I'll try to research this. Thanks.
Yeah.
Okay. Well, I guess it's lunchtime. Well, for me, it's lunchtime. I'm not quite sure what time it is over there. So I guess we can thank the speaker again. Thank you very much, Dmitry. That was
thank you for
very enjoyable talk. So let me just stop recording.